class, some moving around from 1 to 11 o'clock section, but welcome back. I hope you enjoyed your break. How many of you took a J-term class? Anyone? You did? What'd you take?
Gross anatomy.
Oh, I bet that was fun. Kinda. Hard to go in there, but anyway. Did they really bring? No, never mind. Okay. Yeah, I've had students try to get me in there before. Anyone else do anything exciting?
Marine bio took a field trip to Florida for like days.
Oh, so you took marine bio? Okay. Well, that sounds like fun.
Yeah, our oldest son had a 6
I went 6 and
It was tough to come back with 30 degrees.
Did you get to scuba dive or anything?
We went snorkeling with the goal of seeing manatees. We didn't see any because it was too warm, but we did see a couple snouts come out while we were on the boat.
Wow. That sounds like a lot of fun. I've always wanted to snorkel, haven't ever, but it sounds like it'd be fun. Anyone else do anything? Enjoyed their time off with family and worked a lot and all that other stuff, which is, it's good to have a good break. So how many of you remember anything from Organic 1?
a thing or two.
A thing or two? At least one of you does. Okay.
Suckers.
All right. Well, let's go through the syllabus. It's not much different than Organic 1's syllabus, but we'll go ahead and go through it. So in this, what we're trying to do is we're going to just build on what you learned in Organic 1. And when we're looking at it, we're really going to start looking at reactions a lot more. In fact, the majority of what we're going to be doing are reactions and spectroscopy, okay? And how do we analyze these? So those are the two main things that we'll really be focusing on. The main functional groups we'll be talking about are aromatics, and then we will also look at, I wonder if I can get that any bigger at all. No, they have given us a wide screen. That might be a little better, maybe not. And just found out that we got a new screen, and so this is, we're not gonna have, until I can get everything kind of switched over, it's gonna take a little while, might not be quite as good. Can you see it okay? Okay. So anyway, we're gonna look at aromatics, we're gonna look at ethers and amines. Anyone remember what any of those are? Okay, all right, because you need to know that. Alcohols, and then we'll be looking at the carbonyl compounds. Anyone remembers? Can anyone tell me some of the carbonyl compounds that we're talking about, the functional groups? Fall under that heading? Okay, anything else? Good, you got one. Anybody else? Ketones, another one. Anyone else? Aldehydes, okay, anything else? Esters? Remember esters, amides, anhydrides, acid chlorides? Okay. We'll also be looking at some heteroatom type ones as well. So in this point, again, we're going to be looking a lot at spectroscopy and how to interpret. In fact, we ended last semester on NMR and we kind of did a quick run through, and so this semester we're going to go through and take just a little bit more time on NMR. Your lab's going to have a lot of NMR in it, and every chapter, almost, not everyone, but almost every chapter will end with a spectroscopy section of how you would know that particular functional group. So we're going to be hitting NMR and IR and mass spec a lot more. Okay, so what are the general objectives? Well, we want to extend your foundational knowledge of organic chemistry, and so you'll become even more fluent in it. So when somebody asks what are some carbonyl functional groups that contain carbonyls, you'll be going like this on them, okay? We're also going to look at spectroscopy some more, infrared, IR, is IR, nuclear, magnetic, and mass spec. We're going to basically go back and try to, we've been looking in first semester, we were trying to set some foundations that we would then build on, and so such as mechanism and things like that. So we're going to look at how we're going to actually use those when we're applying it to these functional groups. And we want to relate it a little bit to biochemistry, and then again just come to know more about the insights of organic chemistry to society. Textbook hasn't changed. It's still the 9th edition of Organic Chemistry by McMurray, and a lot of you have already gone ahead and registered for OWL. A few of you haven't. If you haven't, please do. We already have assignments in there and everything, so go ahead and get it done. And this in the textbook and materials, it tells you how to do it, but you did it last year, so some of you did last fall, so most of you did. The course keys are there for you if you need those, and I also emailed them to you. If you want a model kit, if you haven't gotten one, we won't be using the model kits nearly as much this semester, okay? We will be bringing them out every once in a while, and so if you want a model kit, you can get it directly through Darling Models, or you can go at the bookstore and get it. Okay. Special projects and activities. We're down to only 5 hours worth as far as service learning and professional development this year, but the technical paper, we've got 8 word process pages, and if you're going to do that, you're going to have to talk to me about your topic by Wednesday on March 11th. So those are in bold, and they'll be due at the same time as if you decide to do the professional development service learning component instead. Those are due on May 6th, so it's a long ways away. Now, if you do the technical paper, I want it to have a lot of organic chemistry in it. I want to see reactions. I want to see structures. I want it to go in depth. I don't want something that somebody who's never taken organic chemistry could write. I want you to use at least 8 primary reference sources in it, and to take on a topic that is worthy for a second semester organic student. Now, got a misspelled word in there. Okay. Need another O in there. Sorry about that. Anyway, we do have, and you don't really know about this, but I think the rest of you do. You can, instead of doing a paper, you can do something called service learning or professional development. And this semester it's worth a little less. It's only going to be worth 58 points, which is 5 hours worth. And for your involvement in it, you get 10 points per hour. I want at least 20, at least, what does it say there? 30% of the points for professional development, at least 30% for service learning, and then the rest can be either. Okay. And you can only get up to 25 points for one activity. So if you do something that takes 3 hours, you only get 25 points. Okay. You have to give me a summary, like you did last time. If you, as it says, if you go to a presentation, you need to state the title of it, who gave it, what the date was, how long it was, and give a write-up as far as what it was about. If you go to a SMACS meeting, again, the date, maybe a little bit about it, and let me, as far as what went on there, how long it was, etc. Okay, if it's a professional development activity, then you need to write up a little bit what you did, the date, what the purpose was, that kind of thing. And you can always email that to me at the end, May 6th at the end. Okay. If there is the undergraduate research symposium at Union, and if you want to count that, going to that, you would count only the hours you spent talking to the chemistry students, okay? So if you go and you spend, 15 minutes talking to chemistry students and looking at their posters, then you only get 15 minutes worth. If you spend 30 minutes, you only get 30 minutes worth. If you, I'm sure some of you might want to talk to some other majors, but I only count what's done with the chemistry ones. And of course, it's all an honor system. Method of instruction. Well, most of you know by now I'm basically going to lecture, do a few demos, not a lot. I'm hoping you'll discuss, you'll ask questions, and of course we have the OWL homework, which you'll love and hate at the same time. Okay. I like it as students actually read through, or I found that students who do their OWL homework maybe a little early rather than late get more out of the lectures, or at least read through the PowerPoints or the chapter, so that you come in here and you have a little bit of knowledge when I start lecturing, and that way you can ask questions if you don't understand anything and know ahead of time what those might be. But if you don't, you can still ask questions if you don't understand what I'm talking about, and I welcome them, and I hope that you do it. It is a 3-credit course, so expect to spend an average of 6 hours per week. Now, I do base the homework on the OWL estimates for that amount and try to keep it a little bit lower than that, but close to it. So a lot of that will be with OWL. Of course, there's always going to be worksheets and all the other stuff. Okay, as far as the activity, homework, that's the mastery and the multimedia, etc., is worth 140 points. The end of chapter quizzes, the EOCs, is 180. So how much does 140 and 180 make? 320. Okay, you're still here. Okay, I know you've had a long break. So, all right. Now 320. Now let's look at this. We'll get back to this in a minute. But here is the point score. What's 1,000 minus 320?
680.
So if you got 100 on everything else, but you failed to do the homework, what would your grade be? Do you think I think it's important to do homework? Yeah, I do. I think it's very important. I think you can learn it, and because of that, I put a lot of points to it. Admittedly, it takes time, but they're points you can get. As you know, these are points you can get. You get 10 tries, and if you can't do it after several and you're getting frustrated, you can come see me in my office. I have office hours, as you saw at the beginning, okay? So, as you can tell, between, how many points did we say the homework and quizzes were worth?
320.
And you add your professional development or your report, what are we up to?
370.
Okay? That helps a lot. Those are points you can get, okay? So please, take advantage of it. They're there for a reason. Okay, now on this one, the first and the fourth hour exams are going to be worth 100 points each. And second and third, there's going to be a 100-point in-class component and then a 15-point take-home component. The reason I do that is that I want you to be able to design a synthesis. And so usually on the take-home portion, it's open note. You can't use the internet. It has to be in your book. Well, you could use them. What you come up with should be in your book. But I want you to be able, and we'll be talking about these different things and how we make them, and so I'll give you something and say, how would you make this, starting with this material, or I'll ask for a mechanism to be drawn out. So those are kind of the two things that fall under that. Usually it's about 3 questions, 5 points each. And then the final exam's 200 points. And what did I say last year about the final exam?
If you got in the 90th percentile, there's an A.
Yeah, if you get in the 90th percentile, you get an A in the course, as long as you kept your homework fairly well up and stuff. So I've had to pay that up a few times, and hope to have to again. So if you just, bomb a test or something like that, but you really understand it and you've gone back and studied it, if you get a 90th percentile, I'll give you the A, okay? All right, now, these are our test dates. Of course, they're all tentative. Notice I say tentatively scheduled. Who knows? One year we even had a massive tornado, so we couldn't quite keep the test schedule. Sometimes we've had snow, things happen. Flu might shut us down a while, but if all goes well, this is what I'm expecting as far as when our test will be, okay? And notice the final, it's going to be, the test 4, it's going to be chapters 22 and 23 and a little bit on 24, not all of it, okay? So that one won't be, 22 and 23 are fairly short chapters, but they're sometimes a little difficult to see. And then 24 is, we won't go too much into it, but we'll go into it some. It kind of depends on how far we get. Okay. You need to be here. Anyone want to remember what I said about attendance last time that's not in here? Because I don't really want to put it in writing as to how it can help you if I see that you're here and you haven't missed. At the end, if your grade is, I'll round up. Yeah, so if you have like an 895, I'll round up. If you have an 890 and you have some homework you can do, I'll have you do your homework, but I'll round up. Okay, I won't round up past that. But usually if you're here, now if you miss once, maybe twice, okay, but if you don't think enough of your grade to come here and do your homework and all this other stuff, then why should I round up? Right? I think your attendance here is very important. And so if there have been people who haven't gotten the best grades because they didn't show up, I would have normally, if they had been showing up, I would have rounded up for them. So be here. I think it's important. Finally, as far as academic honesty, working with each other in study groups, I encourage that. Paying somebody to do your homework, that's cheating, okay? If somebody's over there doing an example and you say, oh, hey, just tell me how to put it down here, that's not gonna do you any good. Know how to do it, take the time on the homework to know how to do it. But work with other people. If you're struggling and there's someone around you can ask, yeah, sure, go for it. On the test, not so much, okay? There's no asking somebody then. But, so no cheating on the test, no hiding cards or writing on your hands or anything like that. If anyone needs an ADA type of accommodation or any kind of accommodation, let me know and I'll come talk to me and we'll work out what you need. And the institutional assessment really doesn't have anything to do with us because it's on Thursday, except for the Thursday labs, but for the class, it really doesn't have anything to do with us. So, but it is going to be, we're supposed to put it in the syllabus, so it's going to be on Thursday, February 20th. Okay, and you'll be getting more information about it. Any question on the syllabus? No? Questions at all? You sure? If you had some questions, then we might start on the material yet. Oh, I can see. You're just all anxious to get started on AMR. Alright. I am going to apologize for this screen. I did not realize that we got a new projector. That's a widescreen projector. And I knew it wasn't working well yesterday, and I didn't realize that we couldn't just get it bigger. But it turns out we've got a whole new wide projector screen, and you can't just go to wide projector screen because it messes your slides up. So it's gonna take me a while to get things redone. Can you see it okay? All right, so we'll just go with it for now. I think it's a lot clearer in some ways, so I'm glad we have a new projector. All right, so our first, what we need to realize is that this time now we're gonna go back. We did it a little bit, but we're gonna go more into NMR, nuclear magnetic resonance. Okay, so we're gonna be looking at it. By the way, everything is still going on Canvas as far as the PowerPoints and the syllabus. This PowerPoint, the student version, and the syllabus are on Canvas right now. Let's see if this works. It works good. Okay, so let's rethink this. We talked about mass spec. What was mass spec about mass spectrometry? Mass spectrometry. It wasn't spectroscopy, it was spectrometry. Well, what did we find out with mass spectrometry? Anyone? You really did have too long a break, you realize that. Well, now most of you just have this, well, let's see, all Thursday people had it yesterday, right? Those in my lab and those in Dr. Johnston's lab. Now surely some of you learned or remembered now what mass spectrometry is. What is it we find out with it?
Molecular size and
Very good. Molecular size and formula. Okay, we're going to take our sample, we're going to hit it with 70 electron volts, at least ours is. There's other ways of doing it. We're going to have it separate out according to its molecular weight to charge, and the charge is always the same for everything. And so because of that, then we can, it's used as our detector in GC mass spec. Because of that, we end up hopefully being able to get the molar mass. It's going to be the end one. Not always do we get it. Sometimes we have to use a little different technique. And then we have a spectrum that we can compare out to a library to see whether or not, to figure out what it is. Okay? So that's what we get from that. Okay? IR. Anyone remember what we get from IR?
functional groups.
Ah, good, you remembered that one. Okay, from IR we get functional groups. We also have that nice fingerprint region, which helps us identify something because it's like our own fingerprints, right? Where they identify exactly me. So when I was in industry, I had a compound that had an infrared spectrum. And the only way, but I could tell the difference between it and something else was that one had this little tiny hump on the side here, and the other didn't. That's how precise it can get, where sometimes that's all you're looking for. But yeah, you can, and it holds up in a court of law. You know, IR will hold up in a court of law. Because it is so precise. And so we use it to narrow down our functional groups, and then if we are trying to match something out to make sure that it's what it's supposed to be, then we use IR. Okay, uses of NMR. The carbon-hydrogen framework. In other words, how do the carbons go together? What's the structure look like? And again, we're going to use a very strong magnetic field. Now, this in organic chemistry is probably considered, although I really like IR, but this is considered the most valuable because you are able to see how the carbons and whatever else is there go together, hydrogens go together. And it's also used in biochemistry a lot. Now that we've got bigger magnets, we can do even more with it to study protein structure. Okay, so our learning objectives, and yes, we're gonna go through, any of you remember what we did last fall on this? So it's gonna be okay if we go through it again? Okay, all right, so we're gonna start off and we're going to look at it was, oh, wait a minute. No. Okay, was off. There we go. Okay, we're gonna look at, well, first we're gonna start out, we're gonna just really talk about what it is. Okay, we didn't do that last fall. And then we're gonna talk about the nature of the NMR absorptions. We talked about that, the chemical shifts in proton NMR. And then we're gonna get more into the proton NMR, the integration, the spin-spin splitting. And then we're gonna look at proton equivalence and complex patterns and uses, and then we're gonna go into the C13. And then we're gonna do something else that we didn't even look at, and that's the depth C13 NMR. So that'll all be good. Uses, and then the something extra has to do with this, which is MRI, which is NMR on the body, okay? All right, so here we go. What we have to realize is the nucleus. Most of the time in organic chemistry, we're talking about those electrons, right? And so when we're thinking about electrons. When we go with UV visible, we're promoting electrons to a higher energy field, okay? When we go with IR, we're getting these molecular motions that are going on. But in NMR, we are looking specifically at the nucleus, where those protons and neutrons are, okay? And we're interacting them in a very strong magnetic field. And if we put them in a strong magnetic field, what happens is that the nucleus, the nuclei, they're positively charged, and they are going to interact, and they are going to line up either parallel to it or anti-parallel to it, okay? Until we apply that magnetic field, the nuclei are very random. They look like this. They're all over the place. Once we put them in a strong magnetic field, they will line up either parallel or anti-parallel. And then it's like everything else. Everyone remember how in order to promote an electron, you have to hit it with just the right amount of energy? Right wavelength, okay? And it'll go up or it will release that wavelength and come back down, okay? Well, with this, you have to hit it with just a certain frequency, and that frequency will depend on the strength of the magnet, okay? So we're going to then have to, well, we have to know what that is, what that frequency is, and we know it, okay? So that's already been done. You don't have to sit over there and worry about that. And what it does is that it causes the lower state, the parallel, and we're talking about these right here, the red ones, to flip to the anti-parallel, okay, to the higher energy, so they're going against it. And at that point, it's called being in resonance. Why nuclear magnetic resonance, okay, because it's the nucleus, it's involved in a magnetic field, and it comes in resonance with the radio frequency pulse, okay, that we're going to hit it with. And so that's what we're dealing with. Okay, so the field strength. Now, we have in our possession here, and hopefully we've got them working. Dr. Johnston, we should thank him very much. He's been working hard. They've changed all the computers out, and it's just been a real headache. We're hoping that things work for you guys in your lab, okay, because you'll be, fortunately, Dr. Johnston will go first, and then mine will, but he'll have to deal with it first, and that's always nice that I'm not the first one out. Anyway, we have a 60 megahertz one. That's a very small magnet compared to what these other ones, okay? And that's what we'll do a lot of what we're going to be doing on. But then we have a 300 megahertz on down here, okay? So we have a much higher, nicer one over here. And really they vary in the size. And the reason, and we'll be learning this in lab, that you want larger magnets is larger magnets allow you to get better resolution. That's the whole purpose of it. And so, especially when you're dealing with a lot of different atoms there, you need the best resolution you can get. So this is just showing that here is at 200 megahertz. When we're dealing with it, the energy to cause this flip to happen is less than if we went up to 500 megahertz. That's all that chart's showing. In other words, if we have a stronger magnet, it takes more energy to flip it into the anti-parallel state. Does that make sense? If you had something with a weak magnet, it doesn't take much to move it, does it? But if you had something with a very strong magnet, it's hard to move it, harder to move it, and that's all this is saying. Okay, so an example, 4.7 Tesla, and we'll relate that in lab a little bit better for you. It requires 200 megahertz. That's how you get a 200 megahertz. Okay, that's what we're talking about, radio frequency pulse. Okay, so it's going to take a 200 megahertz. And for a proton nucleus and 50 megahertz for a C13 nucleus. In other words, it takes a lower amount for a C13 than it does for a proton to get it to flip. Okay? And that's what it takes to bring it in, and that's the VHF range. Okay? Now, normal field strengths are somewhere between 4.7 and 7 Tesla. The current one, the highest at the time of this book, and they've probably gone past that, but I haven't checked into it, I probably should have, is 23.5 Tesla. You don't go in there with a pacemaker, okay? And you take your watches off. When I was a grad student, had to go teach a lab, I kept looking at my watch and didn't realize that I had it on. I had forgotten to take it off. Yeah, I was late for that lab. It stopped it. Anyway, but I eventually got there. They were wondering where I was. Anyway, so, you know, you don't want your credit cards near this thing. You know, you want to be very careful. You take all this stuff and lay it out before you go to the magnet. Now, when you're at the console, you're okay, but if you go up to put your sample in the magnet, you have to be careful about all this, you know, being around a strong magnet like this. You really have to be around this one. 23.5 Tesla requires 1,000 megahertz of energy for a proton NMR compared to 200 megahertz when we're dealing more with the 4.7 range, okay? Now, we have to realize now that we're talking megahertz, and remember when we're going to go back, let's compare them to IR. They're much, much smaller than those for IR. In other words, we have much bigger wavelengths, where IR is much smaller wavelengths. Bigger wavelengths are lower energy, smaller wavelengths are higher energy, okay? So this is just kind of giving you an idea. Again, here's our electromagnetic spectrum, and we're dealing with right in this range and right in here, okay? So that just kind of gives you an idea about where we're looking in our electromagnetic spectrum. And our wavelength size. Now, we have a requirement. Notice that we always say C13, we never see carbon 12, but yet most of carbon is carbon 12, isn't it? Well, the nuclei have to have either an odd number of protons or an odd number of neutrons, okay? They have even of both, it won't work. Well, what's carbon have? How many protons does carbon have? 6. How many neutrons does carbon 12 have? 6, okay? So that's why it doesn't work, okay? Carbon 13, how many protons does it have? 6. How many neutrons? So now we have what? An odd number of neutrons. So it will show magnetic properties, okay? So there's just about, believe it or not, just about every element you can find one of its isotopes that you can get NMR on. Just about all of them. Here's some examples of ones that work. Notice protons. There's lots of those. That means what? It means we don't need as much sample to get a proton NMR as we do a C13 NMR. We don't have to take as many scans because they're more abundant. These don't work, so we can't get our normal oxygen 16. We Okay, so here's an example, work example. Calculate the amount of energy required to flip a proton in a spectrometer operating at 300 megahertz. And then analyze if the change of the spectrometer frequency from 200 to 300 megahertz increases or decreases the amount of energy necessary for resonance. Now this we've already answered. Does it increase or decrease the amount of energy necessary for resonance? Go from a 200 to a 300, or from 200 to 300.
Increase.
You have to increase it. Okay, so that we've already done. This is just out of the blue, isn't it? We haven't done any calculations. Anyone have any idea what formula we're going to use here? It's been a while, hasn't it? Well, I've been teaching physical science all January term, so we've been going over some of these, okay? But this comes from chapter 12. And I didn't copy very good. But anyway, the speed, I didn't show up in mine at home like this. But this is the wavelength, is what? The speed of light divided by the frequency. Okay? So when we're looking at it, we're going to have to figure out our wavelength. We know the speed of light is 3 times 10 to the 8th meters per second, okay? And then we have our amount of energy of one photon, our energy now that we're looking at. We had this equation back in 12.5. And so basically we're going to take our wavelength we have here, that we'll have in meters, and we're going to divide it into 1.2 times 10 to the minus 4 kilojoules per mole. So if you have a calculator and you want to do this, go for it. So what do we use for frequency? Be what, 300 megahertz? We have to do some conversion there. We will, won't we? Okay? No one's getting calculators out, so you want me just to show you how it looks? Okay. We'll get there. So what we see is that here we have this, and we realize that frequency is in hertz, so we have to convert it 300, so basically we're converting 300 megahertz to hertz. Remember, hertz unit is what? Per second? So our seconds cancel out, and so what do we end up with is meters. Okay, so now, when we're looking at that for 200 megahertz, we've just simply put what? 200 down here, which is 1.5 meters, okay? Now we take our equation here, we put our 1 down here, because that's what we need to put, is our wavelength, and we end up with 1.2 times 10 to the negative 4th kilojoules per mole, or it'd be 8 times 10 to the minus 5th kilojoules per mole for 200 megahertz. Which one of these requires more energy?
300.
The 300, yeah. Talking 10 to the minus 4th versus 10 to the minus 5th. So let's go on. We never stop in organic, as you'll all learned by now, I guess, or you will learn. Okay. So what we see is that anyone kind of remember this? Now this we did do. I know, it's been a long time. Okay. You'll get very familiar with this over this semester. What we have to look at is, at this point, we said that all hydrogens, we're going to have to, if we're doing a proton NMR, we're going to hit it with a certain, we're going to set our magnet at a certain strength, and we're going to have to hit it at a certain radio frequency. And if that's true, then all hydrogens are going to what? Do what? Be the same. So how do we get carbon-hydrogen framework? Same with carbons. Well, it has to do with shielding. And what, anyone remember what I talked about with shielding when we talked about it last semester?
Is it like in groups of equivalent, like hydrogen? Oh,
Well, we talked
Yeah.
about that, but on shielding, I talked, imagine that it's you remember, a nice sunny day, right? And, we're having a picnic. And, doesn't that sound like nice? That sounds nice right now. Are you getting tired of all of this gloomy weather and everything? And so we're sitting under a shade tree with a picnic table, and then other people are out playing. What do you like to play out there?
cricket.
Cricket? Okay, we're playing cricket. We don't know how to play cricket, but we're playing cricket out there. Okay, so who's getting more sunlight on them? Those under the shade? Those that are kind of on the edge of the shade? Or those out in the full sun? Full sun, okay. So this is what we're dealing with. We have to realize that we might all be out there at the same time having this picnic, but there are different environments. So now let's relate that to how atoms look, okay? Now, what is it that's causing the shade in a molecule or for an atom? Electronegativity, the electron cloud, okay? So it's kind of shading everything if all things were the same. But how do we do it so that not all things are the same? The electronegativity, right? So in other words, if you have a carbon that is next to a hydrogen, it's going to be pretty evenly dispersed. But if you have a carbon next to an oxygen, what's that oxygen going to do? It's going to pull that electron cloud towards it, meaning it's going to be more shielded or de-shielded? De-shielded, because it's going to have less shielding, isn't it? Okay? So when we're dealing with this, over here is shielded. Over here is more de-shielded. Okay? In other words, these are getting these are getting a normal amount. But if these oxygens are pulling those electron clouds closer to them, then these are going to get more like in the sunlight, you know, especially this one here. That's going to get more like what we're talking about, the sunlight. And so here for the carbon here, you can see for this one here, it's way over here because look at, I mean, it is very de-shielded, isn't it? It's got an oxygen, it's got a double bond oxygen here. So it's going to have a lot of its electron cloud pulled away from it. And this here is going to be pulled some too. Okay? Now, notice that from 0 to 10 parts per million is, and it can go up to 12 or even 13, if we see that, we know immediately we're dealing with hydrogen, proton NMR. When we say proton NMR, it's hydrogen, 1H, hydrogen NMR, okay? Well, if we go from 0 to 200 or even 220, that's going to be carbon NMR. So that's how you immediately know what you're dealing with. You look down here. Anyone remember why we have all this noise down here in the carbon and not in the hydrogen? Because there's very little C13. So you have to do a lot of scans, have it a lot more concentrated because noise is random, signal is not. So if you did the same number of scans on both of these, which you wouldn't do, this you would probably just about not be able to see because there'd be so much noise there and you'd have to do a lot of scans. Noise is random, signal is not. That's more for a lab. Okay. When we're dealing with absorption frequencies, we know that they differ across the hydrogen and the carbon, and I've already talked about this. This is what we just talked about as far as shielding. And so we see that electrons surrounding nuclei have to counteract that external magnetic field. And so it depends on how much shielding there is and de-shielding based on the atom's environment. Okay, so how do we take an NMR? Those long tubes when you checked in and when you haven't checked in, okay? But you did last semester. We had those really skinny long tubes with a colored cap on the top. Those are NMR tubes. So what do? We take a little bit of our sample in there and we dissolve it in some kind of a deuterated solvent. Well, by deuterated solvent, I'm talking about what? D2. And we're gonna use CDCl3, okay? And what we can say is that the deuterium will not absorb, okay? At that point, it's not going to absorb. They'll have a small amount of impurities. There'll be some CL3 in there, very small amount, so we know where that will fall. But most of it's not gonna absorb. And so that way we don't get everything swamped out by it. So we don't see that much as far as our solvent is concerned. In proton, it's around 7.2, and in carbon, it's about 77 point, kind of varies, same place. Okay, so what we do is we put it in the gap of a magnet. We put it in there and take it down to this gap of this magnet. We spin it so everything's equalized out. And then we hit it with that radio frequency energy and we detect a signal. So what we see is that the absorption of the radio frequency energy is monitored by a detector, and it is going to give us our signal. So again, they are aligning themselves up to that magnetic field. They get hit with that specific range, I'm sorry, a range of radio frequency pulses that are known to be what we would need to get the full range for the different electronegativities that we are dealing with, the different amount of shieldings. It's varied. It's going to cause them to resonate, to flip in a slightly varied field, and we can take that and we can get a spectrum out of it. So this is what it pretty much looks like. Here's our radio frequency generator. Here's our sample, and this is not accurate. You only put about this much in your sample, so really this should be moved up in here. But anyway, they hit it with the radio frequency pulse, have a detector and amplifier, and get a spectrum. Now, NMR and IR timescales are different. IR, we can get a spectrum in about 10 to the negative 13th seconds. It can be pretty fast. NMR, it's about 10 to the negative 3 seconds, so it takes longer. And because of that, we can get this blurring effect, and we can actually use it. We won't do this, but we can look at activation energy. So that's just something you can look at using NMR. All right. Let's call it quits, and we'll do this. We'll think about this one, and we'll talk about it. I hope you enjoy your weekend.